Artificial intelligence has a massive problem. And it's not the algorithms or the data, it's the electric bill. Today, we're going to unpack a wild new kind of chip that uses light, yeah, actual light, to tackle AI's frankly unsustainable appetite for energy.
So let's talk numbers. By 2030, the world's data centers are on track to burn through this much electricity in a single year. Now, that's a huge number, so what does it even mean? Well, it's more power than the entire country of Japan uses right now. And the driver for this absolute explosion, you guessed it, AI.
Look, this isn't just about being green. It's about economics, it's about technology. We are literally facing an energy wall that could slam the brakes on AI development. So, the billion-dollar question is, how do we get around it? All right, let's get into Act 1, the problem itself. To really get why this new tech is such a big deal, we have to understand why our current approach is failing. And it's not just that AI is getting bigger and hungrier. The real issue is that the very foundation of computing for the last 50 years, well, it's hitting a brick wall. You've all heard of Moore's Law, right? For decades, it was like magic. We just kept shrinking transistors, packing more onto a chip, and boom, computers got exponentially faster and more efficient. But that magic is running out. We're now down to the scale of individual atoms, and at that level, physics just says, nope, the free lunch is officially over. And if the end of Moore's Law is bad, this next part is the real killer. It's called the von Neumann bottleneck. Here's the deal. From day one, we've built computers with the processor over here and the memory way over there. Imagine a chef who has to run to a separate pantry for every single pinch of salt, every peppercorn. It's incredibly inefficient. In fact, in modern AI chips, up to 80%, yeah, 80, of the energy is wasted just shuttling data back and forth, not on the actual computation.
So what does that waste look like in the real world? Well, take a look at this. Your standard desktop CPU might pull about 150 watts, but the beastly GPUs we need for AI, they're guzzling 1,200 watts each. That's an 8-fold jump. And all that power turns into heat, which means you need these enormous energy-sucking cooling systems just to keep them from melting. It's a truly vicious cycle.
Okay, so if cramming more electrons into smaller spaces is a dead end, what do? We need a new path entirely. Enter photonics. We're talking about computing with light itself. Instead of pushing electrons through copper wires, we're sending photons, particles of light, down tiny pathways. It's a totally different way of thinking, and it just might be the shortcut we desperately need. Now, to really get how this breakthrough works, we're going to step away from the lab for a second. I want you to imagine you're an art detective. Your mission is to find one specific, unique brushstroke that an artist uses in a giant, complex painting. This is a classic pattern recognition problem. And guess what? It's pretty much exactly what AI vision models spend all their time doing. So, how would you do it? Simple, right? Step 1, you'd get a special magnifying glass, your filter, that's designed to only highlight that exact brushstroke. Step 2, you'd patiently slide that magnifying glass over every single inch of the painting. And step 3, you'd make a new map, marking down every single spot where you got a hit. You've just pulled out a key feature from a sea of noise. Okay, that whole process, the filter, the sliding, the mapping, there's a fancy math term for it, convolution. And this one operation is the absolute workhorse of AI vision. It's also the most computationally intense, power-guzzling part of the job. So if you can solve the energy crisis for convolution, you've pretty much cracked the whole case. And here's the mind-bending part. This new chip doesn't calculate the answer in the traditional sense. It doesn't force electrons through billions of logic gates. Instead, it lets the laws of physics do the heavy lifting, for free. The computation just happens as light passes through it. It's baked right into the hardware.
Okay, so enough with the analogies. Let's pop the hood on this thing. We're talking about a real device announced back in September 2025 that actually does this. This isn't just a white paper, it's a working chip that proves this radical new idea is possible.
So how in the world does it work? Well, in a nutshell, first you take your data and encode it into a beam of laser light. Then that light passes through a specially designed lens, which does something incredible. It performs a piece of math magic called a Fourier transform. Now, here's the secret sauce. That transform turns the nightmare math of convolution into a simple multiplication problem. A second lens then flips it back, and a light detector just reads the final answer. The hardest part of the problem just gets solved by physics, passively, as light just does its thing.
Okay, but does it actually work? Well, the results are kind of nuts. On standard AI tests, it hits 98% accuracy. That's basically the same as the top-of-the-line GPUs that are chugging power, but here's the kicker.
The core efficiency is over 100 times better. It can even process several streams of data at the same time by using different colors of light. And maybe the most important part? It's made using the same manufacturing processes we already have. This isn't some exotic lab material, it's designed to be mass-produced.
All right, for the engineers in the audience, let's get a little more technical. Most other attempts at photonic computing use what's called an active mesh. Think thousands of tiny tunable parts that all need constant power and endless calibration. It's a nightmare. This chip, though, is passive. The lenses are just etched into the silicone. They don't move, they don't need constant tweaking. That makes the whole design ridiculously simple, much more robust, and way more energy efficient.
So let's zoom out. A breakthrough like this isn't just a cool lab experiment. It has the power to shake up entire industries. We're talking multi-billion-dollar markets, and it could even change the game in geopolitics.
And believe me, the market is screaming for something like this. The overall silicon photonics industry is already projected to hit something like $15 billion by 2032. Data centers are absolutely desperate for a way to break out of that vicious power cycle. The demand is already there, waiting.
This is where things get really interesting from a global strategy perspective. Right now, the so-called chip wars are all about who controls the absolute latest, most advanced manufacturing equipment for making tiny transistors. But here's the twist. This kind of photonic chip doesn't need that bleeding-edge tech. It can be made on older, more accessible equipment. This could completely change the game. It might not matter who has the smallest transistors if someone else can just sidestep the whole fight with a smarter optical architecture. But for all the talk about massive data centers, maybe the most exciting place for this tech is in the small stuff. I'm talking about putting real intelligence into the devices we use every day. We're talking about AI at the edge. Just think about a self-driving car. It sees a kid run into the street. It can't upload that video to the cloud, wait for a server to analyze it, and then get the answer back. It needs to react now. It needs instant decision-making on very little power. Same for a medical implant monitoring your heart, or delivery drone navigating a city. A photonic coprocessor is tailor-made for this. It's the key to unlocking powerful AI right there on the device, no cloud required.
Okay, let's pump the brakes for a second. We need to be realistic. This isn't a magic bullet that solves everything overnight. There are still some major hurdles. For one, you need to figure out how to do the other parts of an AI network in pure light, not just convolution. And since this is an analog system, not digital, you have to deal with noise and interference. And then there's the massive engineering challenge of actually packaging lasers, lenses, and electronics together on a single chip, reliably and at scale. That's a huge puzzle to solve.
So let's boil it all down. What are the key takeaways here? Number one, photonics is a direct assault on AI's energy crisis because it basically turns math into a physical process that happens for free. Number two, this specific lens-based approach is not just a theory. It works, it's accurate, and we can actually build it. And number three, the next big mountain to climb is figuring out the other parts of the AI puzzle in an optical way, and then integrating it all into a practical system.
And all this leaves us with a really big question for the future. This chip is a genius at AI vision, but what about language? How long until a similar optical trick can be used to speed up the massive models behind things like ChatGPT? As we move forward, the metric for success might not just be about raw speed anymore. It might be about something much more fundamental, how much energy it costs to think. And the answer to that is going to shape the next decade of AI.